up a single teaspoon of matter from the center of a neutron star and set it on your kitchen table. It would weigh about 1 billion tons, and after 60 years of studying these objects, no one can tell you for certain what that teaspoon is actually made of. A neutron star is what's left when a star far heavier than the Sun burns through its fuel and its core collapses. Gravity crushes more than the Sun's entire mass into a sphere about 20 kilometers across, roughly the size of a city, and denser than an atomic nucleus. The surface gravity is around 200 billion times what you feel on Earth. A marshmallow dropped from above would strike with the force of an atomic bomb, and all of it plays out on something you could drive across in minutes. From far away, we can measure the outside. Radio dishes time the pulsars, X-ray telescopes read the surface heat, and we can weigh a neutron star precisely when it orbits a companion. But the core stays sealed. No signal ever leaves it. So what's there, we have to infer. And not every neutron star is a tidy spinning pulsar. The Magnetars are neutron stars wrapped in the most powerful magnetic fields known, roughly 1,000 trillion times stronger than Earth's own magnetic field, strong enough to distort atoms into thin needles. On the 27th of December 2004, a magnetar named SGR 1806-20, about 50,000 light-years away, unleashed a flare of gamma rays that briefly outshone the full moon and disturbed the upper layers of Earth's atmosphere. It lasted 1/5 of a second. Others just sit and cool. The isolated neutron star RxJ 1856, only about 400 light-years from us, sends out no radio pulses at all. Only the faint thermal glow of a surface still bleeding away the heat of its birth. That cooling carries a clue. When astronomers watched the young neutron star inside the Cassiopeia, a supernova remnant, it was shedding heat faster than expected. A sign its interior had just turned superfluid, with neutrons flowing at zero friction. Below the surface, matter arranges itself into shapes physicists call nuclear pasta, sheets, tubes, and blobs of packed nuclei, thought to be the strongest material in the universe, around 10 billion times harder to break than steel. Deeper still lies the real mystery. To know what a neutron star is made of, physicists need its equation of state, the exact link between pressure and density in the core. Nail that down, and you know how heavy a neutron star can grow before collapsing into a black hole. The first suspect is the one that names these stars. Neutrons. Squeeze atoms hard enough, and electrons are driven into protons, leaving a sea of neutrons crushed together. Their refusal to be packed any tighter, degeneracy pressure, holds the whole star up. That holds near the surface, but past about twice the density of an atomic nucleus, pure neutrons stop being a safe bet. Heavier particles become cheaper for nature to create, starting with hyperons, heavy cousins of the neutron, each carrying a strange quark. Hyperons bring a problem. They soften the equation of state, soaking up energy that would otherwise resist gravity. The softest hyperon-rich models predicted a neutron star could weigh at most about 1.5 to 1.7 times the Sun before caving inward. Then the scales spoke. In 2013, a team led by John Antoniadis weighed the Pulsar PSR J0348 plus 0432 through its orbit with a white dwarf and found it sitting at about 2.01 solar masses, heavier than those soft models could ever hold up. That's the heart of the Hyperon Puzzle. Theory insists hyperons should form at these densities, but if they do, they should soften the core so much that a 2 solar mass star couldn't exist. And yet we've just weighed one. Something stiffens the core back, and no one agrees what. A second, independent measurement backed it up. NASA's NICA instrument on the International Space Station timed X-rays from hotspots on the Pulsar PSR J0740 Pulse 620, fixing it near 2.08 solar masses with a radius of about 12.4 kilometers. Together, those heavy pulsars did real damage to the suspect list. Any equation of state that can't support 2 solar masses is simply wrong. The softest Hyperon-dominated models and the simplest kaon condensate models fail outright. They'd collapse such a star into a black hole. Then, in 2017, we caught 2 of them colliding. LIGO and Virgo recorded the gravitational waves from event GW170817 as 2 neutron stars spiraled together. How much each star was stretched by the other's gravity depends on the equation of state. And the signal favored more compact stars, ruling out the largest, stiffest models. So a middle suspect survives. Push the density high enough, and the neutrons themselves may dissolve, their internal quarks breaking free into what's called deconfined quark matter. Quarks roaming loose, no longer bound into separate particles. A star with a normal neutron shell wrapped around a quark matter core is called a hybrid star. Oddly, that transition can stiffen the equation of state at just the right depth, possibly rescuing the 2 solar mass limit the Hyperon models could never reach, which leaves one last suspect, and it's the strangest of them all. In the 1970s and 80s, Arnold Bodmer and Edward Witten proposed something radical. Matter built from up, down, and strange quarks together might not just survive inside a neutron star, it might be the true lowest energy form of all matter that exists anywhere. If they're right, the ordinary matter you're made of is only metastable, stable enough to last billions of years, but not the real ground state of the universe. A neutron star could be a single, solid drop of strange quark matter, a strange star. And a stray fragment could, in principle, convert normal matter it touched into more of itself. It sounds like fantasy, but it makes concrete, testable predictions. A genuine, strange star should be far more compact than an ordinary neutron star of the same weight, or could even exist below the minimum mass at which normal neutron stars can form. So astronomers scan every measurement for an object sitting where no normal neutron star should be able to. In 2022, a team led by Viktor Doroshenko reported exactly that kind of oddity. The compact object buried in the supernova remnant Hess, J1731347, came out at roughly 0.77 times the Sun's mass, and strikingly small, lighter than the theoretical floor for forming a neutron star, and a live candidate for being a strange quark star instead. Physicists also chased the answer on the ground. Colliders like Brookhaven's RHIC and the Future FAIR facility in Germany slam heavy nuclei together, recreating deconfined quark matter for a fraction of a second, briefly forging on Earth the same exotic state that may fill a neutron star's core. The sharpest test still lies ahead, in collisions. When 2 neutron stars merge, a sudden change into quark matter would stamp a distinct signature onto the gravitational waves that follow. Next-generation detectors like the planned Einstein Telescope and Cosmic Explorer are being designed precisely to catch it. For now, even the strongest hints stay contested. That Hess J1731 result is far from settled. The mass hinges on the object's estimated distance and surface temperature, and other groups argue it could still be an ordinary, if unusually light, neutron star. A single measurement, however tantalizing, doesn't overturn the suspect list on its own. Even the numbers we trust most carry quiet uncertainty. 2 independent teams analyzing the very same NICA data on PSR J0740, one led by Thomas Riley, the other by Cole Miller, arrived at slightly different radii. It's a reminder of just how hard it is to read the inside of these stars. So the investigation stalls, with the case only half closed. The heavy pulsars killed the softest Hyperon and Kaon models. GW1000 van Oedidudsansven trimmed away the stiffest. What remains? Hybrid stars, deconfined quark cores, and outright strange stars sits crowded together in the middle, and none of them is ruled out. It leaves us somewhere genuinely strange. We can weigh one of these stars to within a few percent from thousands of light years away, and still cannot say whether its heart is packed neutrons, a soup of liberated quarks, or a form of matter more stable than we are. The open question is whether matter has a hidden lower ground state that only shows itself under a neutron star's crushing weight. And if it does, whether the atoms in your body are truly permanent or just the most stable arrangement that ever had the chance to form. No instrument has ever seen inside that core, and until one catches a merger mid-collapse, 60 years on, the answer is still anyone's to argue.